University and BIMSA, who will talk about quantum integrable systems on integrable classical background. Please.
Thank you. Thank you. So actually, I think many people in this audience already heard this talk several times, but I hope it's improving and improving and improving. So the goal is to explain what a hybrid quantum integrable system is. So the plan is first I will explain what a hybrid quantum system is, and then what a hybrid integrable system is, the relation to deformation quantization. So now it will look very exotic, but then if you see how naturally they appear from deformation quantization, then it sort of becomes more natural. An example is spin Calogero-Moser system and so-called dynamical version of Haldane-Shastry model. Haldane-Shastry model is a model for large range spin interactions. Calogero-Moser system is one of the well-known integrable systems with very interesting mathematical content. It's a joint work with Nicolai Reshetikhin and Ivan Sechin. And so what is a quantum system with on integrable background? So in physics, it's well known. It goes back to the ancient 20th century. So it's called in physics Born-Oppenheimer approximation. It's when the atoms as a whole are treated as classical particles because the nucleus are so heavy. And then the electrons are very light. So the quantum mechanical kind of dynamics around this classical nucleus, that's exactly the quantum mechanics in a classical background. Well, the other possible place where such systems will inevitably naturally appear if they didn't appear yet, it's in quantum computers. If you think about what quantum computer is, it's a very low energetic system where the main problem is to make it stable. But classical interface, the humans, so they will be at the classical level. So it's inevitably, this is a system consisting of two subsystems, classical and quantum. So the other is very famous piles instability. So and then the list is very long. So I'm just saying that it's a natural physical setup. Mathematically, it's the following. So if you have a symplectic manifold, which is a phase space of some classical Hamiltonian system, so we want to have a quantum system which is driven by a classical system on this phase space. So naturally, as you move along the phase space, over each point you have your space of states, the Hilbert space of a quantum system, but this Hilbert space, strictly speaking, is changing from point to point. So they are isomorphic, but they may be different, which means that you have a vector bundle over your symplectic manifold. And let's assume here for simplicity that the fibers are finite dimensional. In reality, of course, they are Hilbert spaces. And by saying Hilbert spaces, I mean Hilbert spaces. So the fiber is some kind of. So right now I'm describing the bundle of hybrid observables. So over each point, you have the matrix algebra of operators acting in that Hilbert space. So it's a star algebra, and let's assume that it's simple. So then the algebra of hybrid quantum observables is Sorry. This way. The topology is complicated, so yeah. so the algebra of hybrid observables is the algebra of, let's say, smooth sections of this bundle of algebras. Naturally, it has a pointwise multiplication, associative. It's a star algebra for this star operation that exists fiber-wise. And naturally, the center of this algebra is isomorphic to functions on M times the identity. The identity is the unit section of this bundle of algebras. So on the center, since it's isomorphic function on functions on M, we have a natural Poisson structure. And the whole algebra is a module over this commutative algebra. But we want a little more. We want to lift the classical dynamics to this bundle of hybrid observables. For this, we need a Poisson bracket between generic sections and central elements. So, so this Poisson bracket, simply you can use again the Poisson tensor, and just you need an extra data, a connection on this on the phase space, and then the Poisson bracket of the central element with any section is just the usual Poisson bracket, where in the second term you use the covariant derivative with respect to this connection. So, so here is the definition of simple hybrid systems. So it's the bundle of algebras with star structure and a Hermitian connection. So that's the kind of mathematical essence of this. And then physically, it's these algebras of observables of quantum systems on a classical background. Mathematically, these are Poisson-Azumaya algebras. So they're well known in Azumaya algebras are well known in algebra. These are algebras that are finite dimensional over the center. So what we add is Poisson structure. Poisson-Azumaya algebras are also well known. Say quantum groups in the Concini-Katz sense. These are exactly Poisson-Azumaya algebras. So, so then I'm repeating myself a little bit, just making a summary. So a hybrid system, integrable system, is an associative algebra, which is simple over the center, and Poisson algebra structure on the center with the trivial Poisson structure, Poisson center, because we require that this spectrum is a symplectic variety. So then Poisson algebra Z, the center acts by derivations on A. So this is the structure. So now we have an algebra. So anyone who is familiar with representation, once you have an algebra, you have to study its representations. There is no other way. So what is the representation of such algebra? So the most natural thing would be to say that, okay, we have a representation bundle, which is a vector bundle over M, where each fiber is a module over the corresponding fiber of the bundle of hybrid observables. In our case, it's a finite dimensional Hermitian space, which is isomorphic to Cn. Our fibers are isomorphic to algebras n by n, and natural compatibility between the Hermitian structure on the algebra of observables and the Hermitian structure, star structure on the algebra of observables, and the Hermitian structure on the representation bundle. So, so as usual, it's a representation, except now it's a fiber-wise representation. So then it's a representation of the algebra. And now let's also require that there is a connection on the bundle V such that it's compatible with our Hermitian connection on hybrid observables. So then on these these representations are a little bit more than we want, in a way that on these representations we will have represented both structure, the associative algebra and this Poisson algebra structure on the center. So again, the center acts by derivations. Well, it acts on this on the sections of this bundle, and this action is compatible with the module structure. So it's exactly what you have if you study representation theory of de Concini-Katz versions of quantum groups at a root of unity. So, but from the physical point of view, this is not natural. It's like you have the this is for physicists. So on M, you have local coordinates P and Q. And if you really want to have wave functions, they should depend on Q only. So at the moment, we have them dependent both on P and Q. So it's a little bit unnatural. So for this reason, let's introduce another notion, Lagrangian modules over this hybrid algebra of observable. So let's fix a Lagrangian fibration on M. Again, it means that the generic fiber is Lagrangian. There could be singularities. So this is basically like fixing an integrable, classical integrable system. So let's assume that we have a Lagrangian section of this Lagrangian fibration. So it's a very rare situation, but let's assume that we have it. So L is intersecting every fiber in one point. So Lagrangian fibration is something like this, and Lagrangian section is something like this. So we have these intersection points. I denote them X, L, B. So in this picture, we have fibers P inverse B. So then it naturally gives a vector bundle over B. Simply we say that of point B, the fiber is the old fiber, but over this intersection point. So this on these sections, A acts naturally. You have a section. It's like again pointwise action, but on V of B, the section A acts like this. You apply A at the point X, LB, at this intersection point. So this action, this structure, it depends on two geometric structures, on this Lagrangian fibration and the section. So I just want to notice that Poisson structure is not represented here. And these sections V of B, this is like wave functions that depend on Q. B here is identically equal to Q. Just use two different notations. Okay, so we have three notions: the hybrid algebra of observables, the hybrid representations, and the Lagrangian representations. So now, if we have a Hamiltonian dynamics, just usual Hamiltonian dynamics, not necessarily integrable on M, so then we can lift it using the connection alpha to the dynamics on A. And then here is the definition: a hybrid quantum Heisenberg dynamic on hybrid algebra of observables is the following. So we have two Hamiltonians. One is classical, which governs the classical dynamics, and that is quantum, sort of quantum twist of this dynamics. And the dynamics is given by this Heisenberg equation, which is sort of the mixture of the Heisenberg equation and the Liouville equation for the propagation of observables, for the dynamics of observables. So this is the definition. And as usual, there is an ambiguity. So if you change the Hamiltonian by some function times the identity, where? So, okay. So then the hybrid Schrödinger picture, it's the same as usual. So there is this. So V is the bundle of hybrid observables. The wave functions here depend on P and Q. So then the sections evolve as we don't have the classical background. This is just the usual quantum mechanics. If we don't have this, this is just the lifting of the classical mechanics to this bundle. But now we have both. So then it's a little bit too much to mix all the time classical and quantum. So we think about it. Let's do something similar to the method of characteristics. Let's consider the evolution of the section at the point xt, which also evolves in time. So then if you do the substitution, the classical part cancels out, but the quantum part should be evaluated at the classical trajectory. So we have the equivalent description. So now we have the non-stationary Hamiltonian, but of the very particular structure. It's a stationary Hamiltonian, but computed at the classical trajectory. So then this dynamics descends to the Lagrangian module and gives the kind of true Schrödinger picture of the hybrid dynamical system, where the wave function depends on. So this is B is like a Q, and the Hamiltonian depends on the point in the phase space, but this point in the phase space is always this intersection point of the dynamics some fiber. So this is the picture. So here xt is the flow line of the classical Hamiltonian connecting the Lagrangian section L and the Lagrangian fiber P inverse B. You see here we have the point P, and the section L is defining the module. So this is what xt is, and this is the picture. So this is how you can interpret it. So this is the Lagrangian. So this is the hybrid evolution in Schrödinger picture in the Lagrangian representation of quantum of the hybrid algebra of observables. So now hybrid integrable systems. So I'm postponing the relation to deformation quantization. Just you will see that everything that I say is very natural. So what is a hybrid integrable system? Classical integrable system is just a Lagrangian fibration, meaning that the generic fiber is Lagrangian. So here is a typical example: harmonic oscillator, generic fiber is a circle, and the singular fiber is the origin. So the usual class of examples is when you have when you fix n global functions on M such that they are independent and Poisson commutative. So then this Lagrangian projection is simply the projection to the values of the Hamiltonians given by these functions, and this the base of this Lagrangian fibration is just some region in Rn. So in general, B can be quite complicated manifold. Actually, it can have some singularities, and typically it should have some singularities. And this H1, Hn would be local coordinates. Okay, so then once we have the, let's assume that we have this formulation, otherwise we use it as local coordinates. So then once you have an integrable system, you don't have a specific designated Hamiltonian, you have n Hamiltonians. And can I just ask, when should I stop? How much time? 10:45, okay. So, sorry, I started very fast, so maybe I'll finish early. So we'll see, maybe not. So once you have an integrable system, there is no preferred Hamiltonian. You can choose any combination of these Hamiltonians, any algebraic combination, and they still will be independent, such that they are independent. They will still be Poisson commutative. So what makes sense is the multi-time trajectory, not just this trajectory of a single particular Hamiltonian. Mathematically, physically, of course, it's a different thing, because these systems, they typically they are models of some physical processes. For this, you have preferred Hamiltonian. But if you study the mathematical structure, then there is no preferred. There are n independent functions. So you have multi-time evolution, multi-time trajectory. That's the most natural thing you can do. And now you have the classical dynamics for classical observables. And a hybrid integrable system is the lift of this multi-time integrable dynamics to the algebra of observables. But now we also twist the dynamics by quantum counterparts, just as we did when we had one preferred Hamiltonian. So in other words, we define the multi-time Heisenberg dynamics of hybrid observables as solutions this system of differential equations. So it's the multi-time hybrid evolution in the algebra of observables. So first term is the lift of the classical dynamics to sections of E, and the second term are quantum twistings. So, of course, it's a system of linear differential equations, so there must be a compatibility condition. So the compatibility condition is the following. So if there is no Poisson bracket here, just like this, so then we know what this is. So it's a flat connection. So sorry, this is T, so this H should be commuted. So if there are no classical Hamiltonians, there is nothing here, there is nothing here. So it means that the commutator should be central. But we do have classical Hamiltonians, so the compatibility involves the bracket between H0 and H1, the bracket between H1 and H0. This is all determined by the choice of the connection alpha. So this is just the usual commutator. And here there's an extra term. So we have two classical Hamiltonians. I denoted to fit the line, I denoted it by F and G. And so we take two Hamiltonian vector fields and contract it with the two form, which is the curvature of the connection alpha. So that's the compatibility condition for the Heisenberg dynamics. But similarly, we can consider the Schrödinger picture. And in Schrödinger picture, we don't have the ambiguity of adding the center, so the condition is more rigid. So in the Schrödinger picture, it's the compatibility condition for the multi-time evolution of the hybrid wave functions. So I emphasize that here it's this funny situation when the wave function depends on P and Q. So the condition is that Poisson bracket of H0 and H1, Poisson bracket of H1 and H0, commutator, and then here we substitute the Hamiltonian vector fields generated by H0 k and H0 j into the curvature of our connection alpha. So this is the hybrid dynamics. And then we substitute, again, use some kind of idea from the method of characteristics. So we compute the section along the classical trajectory. So yeah, this is xt is the multi-time trajectory generated by our vector fields. So then it's interesting. So we have the multi-time evolution for these functions on the phase space, but now it's really like a flat connection. So it's the system of these differential operators, and they must use generically. So I said generically, meaning the following. So if our multi-time dynamics have initial conditions such that it's the dynamic on the n-dimensional Liouville torus, so then we have n independent differential operators and should be a flat connection on this torus. Say, if by any chance we missed generic torus and we choose, say, one-dimensional Liouville torus, so then some of these operators will be linear dependent, and you will have n-1 commuting operators and one differential operator. So basically, this is a flat connection on Liouville tori. So that's how you should think about it. And in the same way as in the usual case of when you have only one Hamiltonian, so it also defines the multi-time dynamics in this Lagrangian module H, where the wave functions depend on coordinate only. Okay. So yes, so I said that this H1, Hn define a flat connection on generic level surfaces of Poisson commuting integrals, but we can drop the word generic, but then some of them will be, but then the torus will be, will have will have dimension less than n, and these operators will still define the flat connection there, but the picture will be slightly different. Okay, so any questions about this setup? So far it's just, it's a rock that falls from the sky, but I didn't explain any relations to anything that we know. Yeah, actually, the first example of this kind of systems I met when we wrote a paper with Babenko and with Bajanov in 1994. It's the discrete quantum Sine-Gordon model at a root of unity. So it has the same thing. There is a discrete classical dynamics on the classical background, and then finite dimensional quantum field theory as the dynamics in the fibers. A very particular trajectory which has a minimum period. It's just, you have a square grid, and the minimal period is the step of this square grid. So this minimal trajectory actually gives so-called chiral Potts model. In statistical mechanics, it's rather famous. So that explains the origin of these strange commutative parameters in the chiral Potts model. They are simply coordinates on this underlying phase space. But at the time, it looked too complicated, and somehow I didn't see the simple examples. And then we started to talk with Leszek and with Ivan, and somehow, as you will see, there is a very simple example, the spin Calogero-Moser that falls in this category. So actually, there is a universe of examples. Many of them are related to quantum unity. It's the well-known stuff. Vanya, you know it from the childhood. You probably knew this before I knew this. So no. Just listen. You have the family of associative algebra. You specify h to h0. So then, on the center of z of h0, actually, I'm going to talk about this. Why am I doing it now? Sorry. That's my next step, the relation to deformation quantization. So let's, if the answer will be unsatisfactory, then I'll come back to this. But it's a well-known construction and representation theory. So now let's assume that the relation to the deformation quantization. So let's say that A0 is an associative algebra. Let's consider the center of A0. Let's assume that we have a flat deformation family of A0, which means that it's an associative, so AH for each H is an associative algebra. The easiest case is when H is a formal variable, so everybody knows how to translate this to this case. So we assume that there is an isomorphism of topological spaces between H, AH, and A0. What exactly it means, it's a long story, and it's much easier to work over formal power series, so then there is no such long story. Equivalently, I put it in the brackets because, in quote-unquote marks, because to say honestly, we need to specify what does it mean, the isomorphism of topological spaces, and which topological. So we have the family of associative multiplications on A0, and this family is the following. So it starts with the multiplication in A0, and then it's a power series in H. It's much easier to think about it as a formal power series, so this is what is written here. So what do you know about it? A well-known fact is that if you consider the skew-symmetric part of M1, it defines the Poisson algebra structure on the center. Typically, this Poisson algebra structure is trivial. But if the center jumps at the point H0, say, if it becomes bigger, then on this bigger part, it's a non-trivial operation. That's exactly what happens for quantum groups at roots of unity. Poisson bracket only on the center. Only on the center. Just wait. So now, also well-known fact is that if you take the Poisson bracket, if you define this bracket at the skew-symmetric part for when Z is in the center and S is any element of A0, then it defines the action of the center by derivations on A. So this thing is canonical. It doesn't depend on the equivalences. This thing is not canonical. It depends on the equivalences, and the equivalences. This is like a gauge transformations of this connection that I was talking about before. Yeah, exactly. So and then there is something that usually people don't pay attention. And actually there is a nice paper by Mikhailov and Vanake where they use this second structure to kind of deform the algebra of the Poisson algebra of the center. So, but anyway, so you take the second part and take the skew-symmetric part denoted by 2, and these are the kind of important structures that you have for free if you assume that you have a deformation. Okay, so now assume that in this deformation family we have a quantum integrable system, which means that we have quantum star commuting Hamiltonians. So that's what people in quantum integrable systems do, and then they look for examples. But now let's assume the following: that in the semi-classical limit, when h goes to 0, when our algebra A becomes A0. So assume that these Hamiltonians, they are very special. They are given, so the 0 term is some central elements H0k from the center Z of A0 times the identity in A0 and some quantum corrections. So, and let's see what this commutator gives in the limit is when h goes to 0. So the first order term is well known. It gives the Poisson commutativity of the classical parts of the Hamiltonians. And if you look at the terms of h squared, so you will have this identity. And actually, you can recognize this identity from the previous discussion. So this is exactly the compatibility condition that we had before. So here the bracket is the skew-symmetric part of M2. And so if you think about it in terms of this geometric data, it's actually, in general, it's a sheaf of algebras with connection. So then we have a hybrid integrable system. So this is the kind of main structural message, that actually there is this class of integrable systems, quantum integrable systems, that have this funny semi-classical limit. So it's like you can think of them as follows. In the classical case, you have functions on the phase space, but you also have, as Vanya said, tensors on the phase space. And so we take into account this tensor structure. Actually, before I go to an example, this, so as you see there, there is this system of differential equations. Everyone who is familiar with the theory of integrable systems will immediately recognize the multi-time M operators in the Lux pair, except there is no Lux operator here. There are only M operators. So the flat sections for these solutions to this differential equation, they must be Baker-Heiser functions for integrable systems. So this gives some kind of new life for Baker-Heiser functions. Now you can think of them as the wave functions for these hybrid systems, and you can naturally ask the question, what will be the star quantization of them? But now let's look at an example. So quantum spin Calogero system. So there are many versions of such systems. So I'll be talking about something that was studied nicely. I mean, it's been known before Hikami and Wadati, but in the work of Hikami and Wadati, it was very clearly written, the Hamiltonians, the commutativity. But now here's the full story that relates this system with representation theory. So there are Cherednik-Dunkel operators, they act on functions. Now, if I say something wrong here, so the author of these operators is here. So, so they act on rational functions. So on Z, they have this structure where K is the permutation operators on Z. These operators, they commute, and kind of nice because they give the representation of the fine Hicke algebra, which is written here. So if there is no this plus one, then it's just a semi-direct product of the symmetric group and the commutative and Rn. But if there is this plus one, then it's something non-trivial. So K gives the action of the symmetric group. So then we have the elementary symmetric functions, power functions, and because these are acting on this space, we can consider the action of these operators on another space. We take the tensor product of the space where the Cherednik-Dunkel operators act, multiply it tensorially with this tensor power of an n-dimensional vector space, take the as an invariant part, and then these operators act naturally on this space. One can take a skew-symmetric part as well, probably any representation, it doesn't matter. So we have, but let's take this space. So then we have differential operators in Z with coefficients that act by permutations in the tensor power of n capital dimensional vector space. So this gives the so Z is e to the iq, and this gives the differential operators, which have very nice physical interpretation. So H1 is just the total momentum. H2 is the quantum Hamiltonian, which consists of the usual kinetic part plus the interaction part. The interaction part involves this permutation of spin variables, and then there are higher integrals, and the existence of the higher integrals gives the integrability of the system. What is it? It's PQ. Yes, it's a type. Thank you. Yeah. So now, as that's one of the typos that I missed. Okay. So fortunately, I can correct it. So then, as h goes to 0, our quantum Hamiltonians, they have exactly the form that we wanted when sort of we were discussing the hybrid integrable systems through the deformation quantization. Classical Hamiltonians of the usual Calogero-Moser system plus quantum corrections. So this is the classical Calogero-Moser system. These are some funny quantum corrections. Yes. When?
Okay, what was it before productivity? Just a little
Degenerate, yeah, this. Yes, it's this one. Yeah, it's if you put letter Q here, so if it will be generate, so this differential operators will be replaced by difference operators, and there is a parallel story for kind of quantum Q, whatever. So then you have these hybrid Hamiltonians separated into the classical Hamiltonians, the usual trigonometric Calogero-Moser system. All the Hamiltonians are derived from the Lux operator, and then quantum corrections, which can be computed easily one by one, and in general, but it's not necessary to compute them all. So what do we have? So we can leave. So we have the classical background, and then we have these operators H1 give this hybrid integrable system. So this is a flat connection of a generic Liouville torus. This will be a flat connection. But now let's look at the generations. So it turns out that there is a freezing point, which has been computed by many people from different angles. So I think we proved it first. I mean, we're still trying to figure out whether it's an original result or whether Fächer, Lasse Fächer already obtained it. Some Rusinax obtained. Okay, so the result is the following. There is a freezing point, the fixed point. P equals 0, Q are equidistantly distributed on a circle. It's the analog of the origin for the harmonic oscillator. It's the fixed point of the multi-time evolution. None of the classical Hamiltonians move this point. So what does it mean? It means that there is no time dependence. So, and it means that you have commuting spin Hamiltonians acting in the tensor power of an n-dimensional vector space. And the second operator is given by this formula. Sum over all permutations is, but then you have divided by sine squared of I minus j divided by m. This is a famous Haldane-Shastri Hamiltonian for long-range spin interactions. The beautiful thing is that it's, so I have to correct. So it reflects the ignorance of one of the authors. So Rusinars. So Simon Rusinars, he proved it first, but it's a long paper, very dense, and every page is like 100 formulas. So it's easy to miss something there. So it's an integrable spin Hamiltonian, nice spectrum, everything can be computed. Physicists use it as a model for long-range interactions and so on. So it has a golden touch, this model, because Haldane got the Nobel Prize for similar work. So it's a Nobel Prize winner model. So then there's a natural question. So yeah, these are there is no H here already. It's a hybrid system, yes. But it's a quantum system in on the spin variables on this extra vector space. So then the question is, okay, so we have the flat connection on the generic Liouville tori. We have this system on zero-dimensional Liouville tori. So what happens with other Liouville tori? Well, and so it turns out that there are n choose k types of degenerate Liouville tori of dimension k, and so over each of these torus there is this hybrid dynamics, and then the next goal in terms of studying kind of dynamical systems. So just construct the eigenfunctions of these differential operators on Liouville tori of all dimensions. And so physically interesting question, one of the physically interesting questions is, say, when you fix k and consider the long spin chain, n goes to infinity. So that's the future. And then you see what happens here is that the base got stratified by points over which you have Liouville tori of different dimensions. Like there is a big open. So typically it happens like this. It's like in representation theory, say if you have a principal Weil chamber, then there is one story inside principal Weil chamber, and the other story is on the walls. And similarly here, you can think of this Liouville tori of lower dimensions as something that's sitting over the walls of the Weil chamber that's the base of our vibration. So the question is whether there is a similar phenomenon for other integrable systems, in particular for the class of so-called super integrable systems. So it seems like we sorted it out, but it's not out yet. So there's this whole array of so-called stratified integrable systems. And actually, it's not an exotic thing. It's a very typical thing. So say, for example, G is simple and compact, then the quotient space, and you want it to be Poisson manifold, but it's not manifold. It's a stratified Poisson space. The symplectic leaves, you want them to be symplectic leaves in the usual sense, but they're not symplectic leaves in the usual sense. They're stratified symplectic spaces. Of course, everything here has an algebraic counterpart, algebra geometric counterpart. And maybe it's these singularity questions are better studied there, but if you look at the dynamical systems, then it's more natural to have a real case, real slice through this algebraic part. Okay, so I think that's all. Thank you.
There were some questions during the talk, no? Okay.
Yeah, I have a comment on the question. So, well, the comment is that you mentioned algebraic context, but in algebraic context, very many integrable systems will produce this quantum integrable systems will produce this hybrid structure when reduced modulo P, because there you have it's kind of formally parallel to root of unity, but it's more canonical.
Yes.
No kind of choices. So interesting. Can be an interesting connection.
Yes. Yes.
And no, the question is so you mentioned that the examples come from roots of unity where you have this extra center, but well, if we have an actual like quantum quantization for like non-formal parameter, and then maybe you have a modulo with this quantized algebra, and then you reduce it modulo at different different roots of unity. And then you get this kind of Liouville tori at different roots of unity. And so is there some way to understand this whole structure, how to interpolate between different?
Right. I think at least for quantum groups at roots of matter what unity you have, the classical count is still the same. It's the dual Poisson-Lie group to the group G.
No, for the algebra, yes. For algebra, it's but for fix a module.
For the module. Yes. But can you say it
Well,
again?
kind of general direction to interpolate basically the story that you're telling.
It's a good question. I don't have the good answer.
means comments rather than questions. You see, when you go to this level, definitely you reach this level. The high is infamous because it has no sense. There's, as Roman explained, right? The small plot rules can be implemented, right? You need special efforts, rules of unity, characteristic P, right? Etc. Etc. So there's a beautiful theory for double language algebra, very much combinatorial, exactly about the description of the sense, right? With many applications on algebra, right? Cubic and whatever surfaces can appear. But it seems, but maybe people can correct me, that nobody tried this hybrid, right? Poisson structure plus this rich structure, right? And good news, what Roma said, that for Daha is simplistic. Not simple, but simplistic, right? There are some functors which connect different groups of units, non-trivial and only at the level of representation here, right? Still, there is some copy. You look at the I'm looking for. Anyway, I wrote the paper. I found them, but they're complicated. I must say. Okay, thank you.
Well, thank you. Yes, I agree with it. Yes.
Other comments or maybe questions?
The eigenfunctions for the quantum system on this strata are good.
Great question. I was going to comment on this, but I'm glad that you asked this. I'm not sure. It's
Can you repeat the question?
the question was how the eigenfunctions of these spin Calogero-Moser systems behave in this hybrid limit. Is this the question? So I don't know. I would love to know, but it's just there was no time. It's an open question. I mean, Lesh, can you comment? Vanya?
It will be kind of generalized object polynomial specialized. It's a special time-dependent trajectories that arise from these low-dimensional terms. It's not explicitly written. We more or less understand how it should look like, but we didn't finish this part of job.
Yeah.
Other questions?
Yes.
It's okay. We can start coffee early. All right, let's thank Colin again.